we'll introduce Earl Mullins here from Mullins Acoustics here in the Valley. He's going to let us know all about the wonderful world of sound attenuation. Board of Governors guys, did I miss anything? Do you need to cover anything else? All right. Hey, wonderful.
So
Thank you, Earl.
open up your USB ports and I'll try and download everything I know. I'm going to pass around a sound level meter here. I'm also going to pass around a handout and business cards. We're blessed with really good attendance today, so I probably don't have enough handouts for everybody. Share for the moment, and I can always get you one by email. It's a PDF, plus it's part of the webinar. And here are business cards, too. I'm based here in Boise. I'm a mechanical engineer by degree and my PE, but all I've ever really done with my life has been acoustics and noise control, 30 years now. I'm almost starting to get it figured out. Can you see okay? Okay. I know I'm a better door than a window, so I could go talk from that side just as easily. One thing I want to say is there are no dumb questions, so if you're thinking it, probably 6 other people in the room are thinking it, so interrupt with questions. Half the time I've anticipated them, I'll say, hang on a second, it'll be the next slide, but don't ever hesitate to ask. I start off with just a little, I call it the brief commercial, but it's my introduction. I work in all these areas of noise control and vibration control. I don't do audio system designs anymore. There was a time when I did some of them, but so I'm knowledgeable, but I don't stay current. I work on just about any kind of project you can imagine. I've done everything from remedial acoustics in somebody's home when they had their 3rd toddler and they got tired of the screaming, to designing a paging system for a chemical weapons disposal facility. And I had to shave my beard and wear be gas mask trained just to be on the facility. I've been in nuclear nuclear power plant control rooms and all kinds of things. Anywhere there's noise or vibration, I have been probably, or will be soon. But these are just the typical kinds of projects I get involved in. You know, it's usually much more mundane. It's schools, it's office buildings, it's some environmental noise analysis and measurement. We'll get into some basics, and that sound meter you're passing around should look real familiar. That's a $300 sound meter. It's good. It's reasonably accurate. It's good for, you know, just quick survey stuff and for passing around. I will loan it to people if you ask politely and promise to get it back to me. But I have a couple of $8,000 sound meters that are much more capable than that. I will not loan those out. But thanks for asking. Sound level is expressed in a quantity that's very mysterious. It's called decibels. And decibels is just a mathematical way of compressing the dynamic range of your ear. When we get to 0 decibels down here at the threshold of hearing, and your ear can actually detect all the way up to 140 decibels before the eardrum starts, you know, mechanically the eardrum starts to break down and the bones inside your ear. That is a ratio of 10 to the 14th power to 1. And just to put it in reference, the national debt is somewhere in here at about 100 or 103 decibels. And your ear can go from 0 to 140. It's an incredible instrument. The way I usually express it is if you had a bathroom scale with the same dynamic range as your ear, you could weigh a single human hair and this, 28-story building we're standing in, all on the same device. So that's a pretty incredible piece of equipment. And I just, you know, we've got some typical levels. For those of you with the sound meter that's passing around, where is it? You're probably hearing my voice. It's reading somewhere in the upper 60s right now, 67 towards 70 occasionally. 62? Okay, I'll speak up. Can everybody hear, by the way? I should have asked that sooner. So I get questions all the time. Well, you know, this is really loud. This must be like 900 decibels. Well, as an experiment back when I was a student and we started learning about decibels, and I took my first noise control engineering course, we calculated the pressure the blast pressure of an atomic bomb at 1 mile, and that came out to 250 decibels. I think the surface of the sun would probably be about 350 decibels if you could ever measure it. So, you know, when people say ridiculous things like, you know, this concert was so loud, it must have been 200 decibels. Well, if it were, you'd probably be vaporized, not just deaf. This is the range of human hearing, and for those of you that work with sound power levels from equipment and data, you see 63 to 4,000 a lot. You also see 8,000. To be honest, in the noise control realm, I worry about 500 and down. I don't even typically spend a lot of time looking at 2, 4, and 8,000 hertz. Usually that stuff takes care of itself. I have to worry about the lower frequency. Like, for example, not to pick on our wonderful hosts, but listen to this room for a second. This is a training room. It's probably pretty close to NC40 in here. There's a lot of rumble. That noise is characteristic of unlined round ducts. I don't even have to see the blueprints. I know what that is. For the musically inclined among us, this is A440 right here, 440 cycles per second. Every time you go up an octave, you double the frequency. All of the speech intelligibility content is in the 500, 1,000, and 2,000 range. Your ability to tell whether I'm saying C, D, T, V, P, or Z is all happening right there at 2,000 hertz. If you lose that, you'll have trouble understanding speech. So you'll hear dBA a lot, and if you look at data, sometimes you'll see dBc. And we use the dBA level. It's basically a filter, a bandpass filter that's applied at really low, rolls off the very low frequencies, and not much in the middle and a little bit in the high, and just a tiny bit of boost there. So the way I usually explain this, I lived in Alaska for many years, and I explain this as in biological terms and survival terms. It's not very important that you hear the distant waterfall or the rumble of thunder from 10 miles away. It's extremely important that you hear the twig snap 15 feet behind you as the grizzly bear is stalking. So biologically, we're programmed to hear the middle and high frequencies much better than the lows. And dBc is just another setting on most sound meters that kind of takes that filter out. And there are times to use one or the other. You've run into the NC, or noise criteria charts, quite a bit. Basically, these are equal loudness curves. So you pick a point anywhere along the curve, like 8,000 at NC 25 is a level of about 26 decibels, and that's equally as loud as 59 decibels at 63 hertz. Now, there are other criteria out there. There's RC, there's PNC, there's a variety of things. I'm a little bit at odds with ASHRAE and the ASHRAE guide these days, because about 10 years ago they kind of went away from NC and RC, room criteria, which is essentially this kind of process, except it just gets stricter down here. Instead of it curving up in an equal loudness manner, it just goes straight across. And all you're doing is you're not changing the noise levels that you're achieving or designing to, you're just having more buildings fail spec. And I've done a lot of work on military bases where, especially the Air Force, for some reason, they have this blanket spec that says all rooms shall be NC 30 or less. And that's not really practical in a hangar that's 800,000 square feet where you're working on a couple of B-52s side by side. You can't ventilate a room like that and have it be that quiet. So I'm not a big fan of RC. NC has worked great since 1957. I've never had a project where we met the NC criteria where we had a serious noise problem or serious noise complaints. I see RC as just an artificial way, but I'm not a technical 2.6. They don't want me. They don't want to hear that. Yes, sir.
Are there some people that have like super hearing that would have noise complaints? You said serious noise complaints that like would have noise complaints that other people don't register, and I just repeat the question.
For the internet, hello internet.
Yeah.
The question was, are there people out there with super hearing? And yes, there are. However, you know, we're in a practical world here. Like I told you a minute ago that this room is probably close to NC 40. if this were the boardroom, Idaho Power, or if this were a serious video conferencing facility, there would be complaints about it. However, for our purposes, I'm close for the internet folks, and nobody in here is more than about 35 feet away from me, and I'm projecting well. It's a little noisier than we would like, but in practical terms, it's good enough. It wouldn't cause a complaint, but one of the things I talk about all the time in terms of noise ordinances and community assessment is there's always going to be somebody who complains about something. We cannot set a level that says all people will be satisfied if we're below that, or a level all people will be unsatisfied and complain if we're above that. So that's a great question. Again, essentially equal loudness curves. And NC15 is what I would design, say, a radio studio or recording studio to. This room should have been about NC30, being a divisible training room, using half of it. If we were using both halves and we had 80 people instead of 60, I'd have to use a microphone and a PA system with this level of background noise. I'm going to run through a lot of this because our time is pretty limited. I could easily do a half-day course just on the slides you're looking at, but I'm not going to keep you captive. You guys are nice enough to come down and listen, and ladies. I often get the question, well, Earl, I've got a mechanical room and it's got a pump in it, and it makes a level, and I've got to put another pump in there just like it as a redundant, or just to, we're building out the building, we need more capacity. If I pump it, another pump that's 60, that's 120 decibels, right? That's serious. Sorry. Decibels don't work that way. If you double the amount of energy, it's added 3 decibels is all. So if you have one pump that makes 60 and you put a second identical pump to it, the level will be 63. Now if you go from 2 to 4, then you go up to 66. You go from 4 to 8, you'll go to 69. And it takes roughly 8 to 10 decibels to be twice as loud as the previous level. That was twice as loud to your ear. It was 10 times the effort for me vocally. So my first question is, do you have a noise problem with the existing pump? You're going to say, well, no, not really. Well, you won't have a noise problem if you add one more pump to that. You might have a noise problem if you add 7 more pumps. So decibels, it's 3 dB every time you double the energy, every time you double the number of sources. However, my invoices are not logarithmic. When I bill for time, it's linear. When we're trying to stop sound from getting from one place to the other, there are a couple of ways to do that. Mass, you can do it. You do it, and some of this bleeds over more into architecture than mechanical stuff, so I may go a little faster. You don't need 8 inches of concrete because I can beat that rating with a double stud wall with 2 layers of sheetrock on the outside of each layer, stud row, and bats and insulation. I can beat 8 inches of concrete pretty easily. Putting absorption on the surface, once the sound gets through, putting absorption on there doesn't do anything. It's like painting the wall blue instead of red. How much does it noise control difference does that make? Not much. And the reason is that the sound passes through once. And even an absorber that absorbs 90%, that's a 3 decibel difference. And when we're talking decibels, the meter can detect a 1 decibel difference. My ear can detect a 3 decibel difference. You can detect a 5 decibel difference, or a little less if you're expecting a change. You're listening for it. And a 10 decibel difference is twice as loud. So if you're driving down the road and your favorite song comes on, you click it up 2 clicks so it's noticeably louder, you just went up by 7 or 8 decibels from where you had been.
Question.
Yes.
So explain that again. You're talking about when you soft material, some kind of panels you put on a hard wall.
If I'm trying to protect sound from the other room coming into this room, putting absorption on this side of the partition won't do very much. Putting some absorption on the other side will help just a little, not worth spending a lot of money on.
What about within the same room?
Within the same room, it doesn't reduce the noise much, It would be the equivalent of, say this wall, all these walls are painted white, and we get a certain amount of illumination from one light fixture. And now let's go through and paint them beige. Essentially the same amount of light is going to reflect around the room. Yes, sir?
You take a gymnasium and putting panels around, maybe hanging them, or they put them on walls in certain areas, maybe some of the comment there, and so on. But I notice they do that. Now, is that just to eliminate echo? Not anything for sound in the gymnasium?
Yes. For the internet, for our webinar friends, the question was putting absorption inside something like a gymnasium. And put absorption in a gymnasium to reverb or echo out of there. We have a drop ceiling in this room, and bodies and the carpet and the chairs to some degree provide a little bit of absorption. That makes this room less echoey. It really doesn't make any difference as to our noise escaping out into the hall or into the next room. So I have a sort of a glib saying about that. Never use an absorber when you need a barrier. In other words, never bring a knife to a gunfight. You got to pick your tool. If we're doing an enclosure, this is couched in terms of walls inside a building because mostly I give presentations to architects. These are the 3 magic bullets. Use dissimilar sides, 2 layers and 1 layer. In case of glass and float glass, because their vibration and resonant frequencies are different. Use the best airspace you can get. A double stud wall is better than a staggered stud wall. 4-inch and a window is better than 1 inch, which is better than a 1/2 inch. And then insulate the cavity, which you can't really do in a window, but you certainly can in a wall. As a rule of thumb, if you're building an enclosure, if you're building a wall, if you're trying to build a barrier to noise, insulation is so cheap, it's pretty much a given. Just do it. You're never going to lose anything by insulating an enclosure or a wall. And here's an example. Basically these 2 systems are the same except for down the middle on the right-hand system. This actually happened to me early in my career. It was really expensive condos. They were almost $1 million in the 80s in San Francisco. And I had this contractor, out of the goodness of his heart, bless his heart, but he really screwed things up. He said, I had a bunch of sound deadening board left over from the last job, and I'm just going to donate it to the cause and put it in. But he never asked the architect, who never asked the acoustical engineer. Hello. And by dividing the air cavity and creating 2 smaller spaces that want to resonate at certain frequencies, you took a wall that should have been very good at STC 63. Basically, on the other side of that wall, you wouldn't be able to hear me talking. And he made one that, the building code says you have to have STC 50 as a minimum for a party wall. So by adding some material, he actually took a great wall and turned it into a mediocre subcode wall. So you got to be a little careful. Sometimes less is more. This is another one that we see all the time. I've been trying to slay this particular dragon the entire 30 years of my career. We have sound going between offices. Let's throw a layer of bats up there, a couple of feet on either side. They're obviously absorptive. They'll absorb away the sound. I've tested probably 700 office-to-office conditions over my career. Not one ever has tested above STC 35, room to room. And if your spec says you got to have 40 or 42 or 45, adding the bats, it's literally a drop in the bucket. It's just not going to do much. I'm going to skip through some of this stuff because it's really not targeted at this audience in particular. But let's say we have a brick wall that stops 50 decibels of sound, and into that brick wall we want to put a window that stops 20 decibels of sound. So what happens here is a little bit of lesser material really lowers the rating. You'd think 50 and 20, and if you go half and half, you'd split the difference, but you always skew very much toward the weakest element. So this particular example is 1/8, only 12.5% of the wall, and instead of being a 50 wall, it turns into a 29 wall. And as the percentages get bigger, you skew closer and closer to what the glass does. I'm not going to read slides to you. You can read. When I'm thinking in terms of noise control, leaks and penetrations are my enemy. If I'm trying to build a sound wall or build an enclosure around a noisy piece of equipment, we got to get air in and out. And a little bit of open area hurts a lot. It's just like if you're building a roof, how much water leakage can you tolerate before it's not a roof anymore? If you're building an electrical circuit, how much short circuit can you tolerate? Not much, and sound is kind of the same way. So if you have a piece of a wall or an enclosure that's rated for 50 decibels and it's got 1% open area, and that isn't much, you can take 15 or 20 probably off of that. Now 1% open area is, you look at this wall over here, not even counting the doors, but the perimeter of the doors, the junction boxes for the various controls, the fire alarm, the clock, all the electrical boxes, that adds up to more than 1% of this wall. So if this, if I design this wall to stop 50 decibels of sound and we put this many penetrations in it, we might, I'd consider myself lucky if I got 35 instead of 50, and more likely to be 30 from here to the outdoor space. So just more examples of things that can hurt us in terms. Now, this is couched in terms of walls again, but it all applies equally to noise control enclosures around a piece of equipment. This is one I like to bring up a lot amongst my mechanical engineering brethren. We go to a lot of trouble to build a wall here that has a good sound rating because of the neck space, and then we put this big hole in it, the air transfer duct. And even though it's lined, it is a big honking hole in the wall, and that's a lot more than 1%. So sound is going to filter through the ceiling tile, which is an absorber, not a barrier. Never meant to be a barrier. It's porous. Sound is going through there and hitting the deck. And some of it is coming back to us, and some of it is skirting over the top of that partition into the next room. So we have to be careful about these things. This is an acoustical boot. It's a lined rectangular elbow with at least 3 feet or 3 duct diameter, minimum duct diameters minimum, and 1 duct diameter here. Now, a lot of times I'll look on drawings and I'll see an acoustical boot and it just cuts off without the duct. It's really just an elbow. And sometimes you can even see through it. It really isn't going to stop a lot of sound from one room to the next. This is how you do it.
U-shaped or just an L?
Well, an L is the first step. And, adding an elbow on the other end, making it a U shape, is the next step. And to go beyond that, you're going to have to use a silencer, like a 3-foot specialty design silencer. And I don't care which way the openings orient. You can have it be, a U in plan. The openings can face upward, one up, one down, one facing north, one facing south in plan view. It doesn't really matter. What happens is as sound comes in through here, you go from an infinite cross-section to a finite cross-section, which incidentally is why the bells of trumpets are curved, is to help that sound escape and match between the two. So you've got a little interference effect going on at the entry. Then sound comes up here orthogonally and hits the surface and bounces back. Then some of it is absorbed and not all of it makes it around the corner. Then you got 3 feet for the sound waves to get in lockstep, marching like a group of soldiers. And then when you get to the end here, you have another end reflection effect. And so that is good enough for walls that are up to about STC 45, which is okay for private offices and low-grade conference rooms. If it's a high-grade conference room or judges' chambers, for example, that's when we add the other elbow. Penetrations. Not to pick on the contractors in the room, but there's something magic about a 1-inch pipe needing a 6-inch hole. I realize I'm not the guy up there sawing sheetrock and hanging pipe, but we've got to repair these things because 1% takes 20 dB off our rating. And I see this a lot of times, you know, piping that has an insulation jacket. We want to interrupt that insulation jacket, caulk the penetrate, you know, reduce it and caulk it, and then start the insulation on the other side. Because insulation is absorptive, but is not a barrier. And I use a submarine analogy quite a bit. If this room were in a submarine and we sprung a leak, what would you rather have? A steel patch to prevent the leak, or big bags of sponges to soak up the ocean before we all drown? Once it gets in, it's bouncing around. You can't absorb all the sound away. You need the barrier. And so the insulation jacket is basically a path by which sound, it's a hole. And the same thing happens in a fluted deck, you know, where we have metal pan deck and the wall goes up to it and you leave those trapezoidal voids. The standard detail is to stuff insulation in those. And that's probably okay for air permeation and fire rating. Does nothing for sound. I've tested it with and without. You know, you can test the wall, go up and pull all that bat out of there and test it again. I get exactly the same number. I need an airtight and or massive, airtight at least, like urethane expanding foam, and massive like a piece of sheet metal or sheetrock or, you know, something to fill it. I'm going to skip a couple of these things. This is an outlet box pad. You know, if we're putting a hole in the wall, the rating quickly goes down because electrical outlet boxes have a lot of knockouts, and you know they're pretty porous. And so you have a case like this slide where you've got, you know, I've had a lot of cases where electrical boxes end up being either back to back or within the same stud cavity, and sound just shoots through, and a wall that a party wall in a condo or an apartment or a hotel should have been 50, tested at 32, just because of some back-to-back junction boxes. So what I like to say is 95% isn't good enough for sound purposes. We've got to go all the way, or else don't bother. Rectangular duct. I'm a big fan of rectangular duct. It has several interesting aspects, especially in wide aspect ratios and thin duct walls. It can rumble, an oil can, and it lets out a lot of rumble. That's not necessarily a bad thing if the rumble is occurring over core space like storage or janitor closets or circulation. It is a bad thing if it's over a training room like this. So by rumbling and that actual physical mechanism of moving the surface of the duct wall, that is a lot like adding absorption. The advantage is it's easily lined. Now the converse is round duct. Round duct acts just like your doctor's stethoscope. It conducts sound. You know, we use round pipe rather than square pipe because of a lower coefficient of friction and smoother flow and less turbulence. Round duct is very stiff, and it won't let the noise break out. It won't oil can, so it's good to use, you know, if the air handler were in the next room and we wanted to span across here without hearing that rumble, I'd like round duct here. But that means it contains all the noise, and there's just more noise going downstream into the next room. Whenever I talk about lining round duct, people cringe and start, you know, sweating and yelling and, you know, throwing things at me. It can be done. It works quite well, but it's expensive. Now, you've all probably heard of K27. And when I say K27, factory line round duct, the people putting together the bids start cringing and going, oh, you just blew our budget. One of the things I like to do, duct lining works pretty well for noise control, but there are a lot of situations where we're not allowed to use duct lining. For example, at Boise State, their campus-wide building spec says, thou shalt not use duct lining without basically Dr. Custra's approval. The president of the university has to sign off. So if you can't use duct liner, our next step is to go this way and use a prepackaged silencer, which is basically a duct segment with baffles inside and perforations, and that's usually full of mineral wool, rock wool. And I show you a picture of a rectangular version and a round version. And they work pretty well. Typical silencer might be $1,500, $2,000, and it'll add a little pressure drop to your system. So, you know, there's a life cycle cost as well as a first purchase cost. I got to throw this slide up because this really did happen. This is actually taken in the John Paul Getty Art Museum in Los Angeles. And you see all this ductwork up here, so you know that the other side of this wall is a mechanical room. And guess what hung on this wall when the museum was finished? A $20 million Monet painting. And people that go to the museum to see something like that don't want to hear a lot of mechanical rumble above their heads. So, this is just a spectacular example of sometimes we don't want certain things next to others. We don't want to put a machine shop on top of a recording studio, and I've actually encountered that. Let's talk about vibration for a second. There are two ways that sound gets from one space into the next. There's airborne sound. I've showed you a pump here that's radiating sound, which transmits through the decking and into the space below. And in many cases, that's a relatively minor path. But if we take and bolt this thing to the structure, and it vibrates, and that vibration gets into the structure, it goes out in any number of ways. And it's been a few years now, but early in my career, I had a building much like this one that had a huge cooling tower on the roof on the 21st penthouse level and a mystery noise on the 5th floor. Nowhere else but on the 5th floor. It was a giant cooling tower. And what happened is we had vibration isolation under the cooling tower. We had vibration isolation between the cooling tower and the piping. And as that piping ran down the shaft, every so often it had to have seismic restraints. And on the 5th floor, they reefed on the cables. They turned the turnbuckles a few too many times and turned it into a taut guitar string. So the vibration that remained from the fluid and got past the isolators was shaking that pipe, which was then tied to that wall. And much like an acoustic guitar makes more sound than an electric guitar that isn't plugged in, it had a radiating surface, it had a soundboard. So it took forever to figure that out. It was quite the doctor's science project. But once we got in there, we figured it out, cut a hole in the shaft wall, went in there and just basically undid the turnbuckles about 3 turns so that they were floppy. The noise went away. But you don't cut into the shaft wall in a fire-rated shaft in a high-rise building casually. Vibration isolators. Springs are a good thing. Pads, cork, felt, rubber, usually not so much. You'll often see them in different colors because you need a different rating for each corner of the equipment because they have a weight distribution. You have a heavy end and a light end. You can't use the same spring on all 4 corners. One end will be too squishy, the other will be too stiff. And I often say that based on experience, no matter how big the piece of equipment, I've had 10-foot in diameter squirrel cage fans that were on big inertia bases and served a whole 20-story building. You should be able to go up and rock them. If it takes a guy my size, NFL lineman size, jumping up and down on the corner of the inertia base or the support network to see any visible movement in the equipment, those springs are way too stiff. And they're passing probably 75% of the energy instead of isolating 90% or more. One of my particular crusades, yes, sir.
Just back on we have a particular building that a rooftop was put on. It's over a classroom, and the classroom is not useful. There was so much noise in that classroom. It's not useful. Originally, they thought there was too much CFM, which there was, but I'm just sort of curious because when we actually go above the drop ceiling, tile ceiling, up in that space you hear no noise. You come down into the classroom and you can just feel the pulse and you can hear the noise. And yet it was sort of odd that you go up above the ceiling tile and it's a metal roof and it's mounted, so there's no isolation pad mounted on the roof. And you really don't hear the vibration, but when you put tile back in, you hear the vibration.
Okay, I can explain that. The web question, for the web, the question was a rooftop air handler on top of a lightweight roof, metal pan deck, and when you're in the room, you could hear it rumbling and roaring. You could hear a lot of noise from the unit, but if you popped the ceiling tile, went up there and stuck your head above the grid, you didn't really hear that noise. So that's not a case of airborne noise transmission through the deck. That's a case of vibration or lack of vibration isolation. So you're shaking the deck, which is shaking the walls, which are then acting like speaker cones to radiate those frequencies. And I often use my, my really expensive diagnostic instrument here. For the people on the web, I'm walking over and putting my ear against the wall. And you hear the noise conducted through the bone better than you can hear it conducted through your eardrum. And if you do that and then you go up on the roof and put your ear against a piece of equipment, you'll often hear those same tones. And they're usually lower frequency. They're usually pure tones. They're something like the RPM of the fan wheel, the blade passage frequency. They're usually discrete tones, not just general broadband air noise. So, and you did say one critical thing in your little description of the problem is that it was just bolted to the roof. It wasn't on isolation. So, bingo right there. And if nothing else, what I try and do is I can't download 30 years of knowledge and 2,200 different projects that I've worked on over the years in an hour. Would that it be so. We'd all be PhDs and everything. But one of my goals is to dispel some of the myths you might have been operating under, and one of my other goals is, what would Earl say? What did he say about that? And just call me up. And I always have 5 or 10 minutes to talk to you on the phone and answer a question. And my rule of thumb is if it takes me longer to take out a job number and develop an invoice than it does to answer your question, I never bother charging for it. I put it down to marketing. So never hesitate to call. If you're calling the 8th time and we've had a couple hours on the phone for the same projects, like, okay, sorry guy, the meter's got to start running here. But if you got a quick question or if you have this nagging doubt, what would Earl say? I'd much rather spend 15 minutes with you every week answering questions and have you build something that's going to be a problem that then costs $50,000 or $100,000 to sort of fix. And that's another thing too. My role as a consultant is when I work with designers, there are times I have to and say, whoa, foul on the play, If you don't do this now, you won't be able to fully fix the problem later. If you may get lucky, and this may be one of the buildings that doesn't have a noise problem, but if it does, it's going to be difficult, expensive, and maybe impossible to fully fix. And yes, sir.
I was just wondering, there's a difference, like triple fillers, two fillers are more of a pure tone, and it's harder to eliminate, and triple is not a non-pure tone. What's the difference between a pure and non-pure?
Okay, the question was what's a pure tone versus basic broadband noise?
Yeah.
Broadband noise is like ocean waves crashing, static on the TV, the babbling brook. It's a wide range of frequencies, low, middles, and highs, fairly even. Pure tones are really distinct, like transformer hum, bearing squeal. An automotive, a fire truck siren is a pure tone, specifically because it cuts through the traffic noise, the vehicle noise, the radio, the kids in the back seat screaming. You hear that siren because it's very loud and it's a very pure tone, and it's designed to get your attention. So yeah, it can be much tougher to deal with a pure tone than broadband noise. So, guys are asking great questions. Yes?
So a pure tone would be a really narrow range of frequencies?
Right. Very narrow, even very specific frequencies. Like, for example, an electrical transformer, 60 hertz power means that we get 2 waveforms per second, one positive, one negative. So the transformer core is vibrating 120 times a second. So 120 hertz is the primary. Then do integer multiples of that, 240, 360, 480, etc. I don't, by the time I solved it at 480, I've solved it everywhere else, so I don't bother to commit those to memory. And while we're here and while we're sitting in the Idaho Power Building, let me pick on transformers for a second. In most buildings, 98% of the buildings I go into, you'll see an electrical distribution transformer, sometimes the size of a home refrigerator, and it's bolted to the floor. Or if somebody thought a little bit about the possibility of noise or vibration-induced noise, it might be bolted to rubber pads, bolted through rubber pads. Now, rubber doesn't isolate below about 300 hertz. So everything below 300 hertz, that may as well be a 2x4 block. And remember, I just said transformers are 120, 240, and 360. So you're into the second harmonic before those pads even begin to work. And that assumes that the guy's actually installing it. You know, you should tighten the bolts so that it's about 25 to 30% compression on the pad. But most of the time, you know, if 80 foot-pounds is good enough, we're going to use 120. And those things are reefed down so that that nice rubber pad is crushed into basically bridge-bearing neoprene, and it may as well be a 2x4 block. In other words, rubber pads don't isolate transformers or low-frequency noise in general from any equipment. This slide that when I first started my career back in the early 80s, this is my 30th year, by the way, it was pretty normal to have an air conditioning unit or air handler, packaged air handler, sitting on 4, 6, 8, 12, whatever it took, external springs. And about 15 years ago, there was a real huge trend to go towards setting the air handler right on the roof and having springs on the internal fan wheel itself. And that works pretty well much of the time. I'm the first guy to say that 80 or 85% of the buildings out there don't have significant noise problems. But if you're one of the unlucky 15%, it's real ugly to try and fix. So if it's just your typical run-of-the-mill office building or warehouse, I don't get too excited. But if you talk about putting an air handler over a classroom, like that earlier question, an air handler over a training room or a conference room, over an auditorium, I'm going to dig in my heels and say, you really need to not use the internal isolation on the fan wheel. You need to put the whole unit on springs. And then, of course, the manufacturer comes back and says, no, our internal springs are great. They work every time. Oh, that's nice. You want to pay the bill for the last guy that, you know, had to have me come in and measure and then had to spend $28,000 getting a crane to lift it up to put the springs on that should have been there in the first place? One of the pitfalls of being a consultant is that, you know, 98% of my projects work just fine and I never hear back. I get calls on the ones where something wasn't done right and, you know, we've got a noise problem that wasn't expected or we thought we had dealt with adequately. And I have to constantly guard against being overly conservative. You know, I can't gold plate every project. You know, I have to be realistic. You know, a high school gym is different than the Carnegie Hall, which is different than the Ann Morrison Center. You know, there's a time and a place. You got to pick your battles. So we already talked about this. The fact that rubber pads don't work for very low frequency stuff. There's a picture of an acoustical boot. Now in this case, there's absolutely no reason whatsoever for that to be on isolation hangers. There is for this big duct, but there's no reason for the boot to be. But I think that, you know, there was just this blanket spec. Every piece of ductwork must be on isolation hangers because there's not a lot of rumble occurring in this, and there's ultimately going to be a wall built across here. So this is what an acoustical boot really looks like in the field, and it's more than just the elbow. Bob?
Why would you recommend, if we've got a piece of equipment connected to the ductwork, we've got, say, a fabric flex connector between the ductwork and equipment, does that not work to take out some of the rumbling you recommend on some, say, a much larger air handling unit? You actually put your ductwork on spring isolation hangers?
The question for the web is, do we go just beyond the fabric flex connector at the air handler? Isn't that good enough? It is in many cases, but you know, as you come out of the air handler and the air is tumbling and turbulent coming down here, it makes the duct wall vibrate. If it's a critical situation, like, you know, the radio studio you and I worked on last year, we're not going to just depend on the fabric flex connection between the first duct and the air handler cabinet. We're going to put the first 2 or 3 hangers be isolators, because there's always a little bit of residual turbulence and a little bit of residual noise, and so those duct walls are actually vibrating. Great questions. Now, here's a case of, you know, just what you asked. We've got the fabric flex connector at the duct, and that's good, and we've got the vibration isolators here, but look what didn't get addressed. We've got flex conduit, we've got spring isolators, and we've got, so this unit is fairly well isolated, but then we got this natural gas or water line piping here that comes in, and that's rigidly connected. So just like 1% leak in an enclosure can hurt you a lot in terms of airborne sound isolation, 1 or 2 rigid connections can really mess up your vibration isolation package. I got to tell this story, and we're rapidly running out of time here. This is the rooftop of Levi Strauss headquarters in downtown San Francisco. And what they did is they had a whole floor of computers, which, as we know, are notoriously, they need a lot of cooling. They're very hot. And so they added a whole nother cooling tower up there. Now this is the final result of a long process, because they turned this cooling tower on, and they discovered that the people in these $700,000 condos were all attorneys. And the property line is the edge of the building in San Francisco according to their ordinance, and that's just right across the alley. That's like 15 feet. And so, there's my sound meter, my old sound meter. And this is the enclosure complete with all the features that made the system work. And so as we go around the corner here off to the right of the screen, oops, and we look at, this is the view to the east, and if we go around here and look at the view to the north, we discover that the people up on the hill, Coit Hill in San Francisco, with these $2 million condos and townhomes with the views, they weren't just lawyers, they're all judges. So Levi turned this cooling tower on, and within hours they were slapped with an injunction. You will turn that doggone thing off, and you'll make it right, or it'll never run again. And we'll send the bailiffs. So what we'll do here is we'll walk up. We're looking at the bank of silencers here, and if one is not enough, you need a bank of them. And they let the air go in, but they tend to contain the noise. So we'll go in up the stairs and turn into the door, and we'll turn to the left, and this is the actual cooling tower itself. Not very big. The thing is like maybe 8 feet by 10 feet, and you saw the size of that enclosure. It was 40 by 80 or something. So what you're looking at here, this is the internal side of the silencers that you saw from the external view, and these are acoustical louvers. This is actually a sound absorptive surface. Now, the one-time sound absorption helps you in terms of noise control is you put it inside the box or inside the duct. It helps a little bit there, and it's like having a light bulb in a room. You put in a 100-watt light bulb, you get a certain number of lumens, but you have a perceptibly brighter room if it's painted white versus painted black. So the absorption is essentially painting the room black. This is an acoustical louver, and what it does, it's an airfoil-shaped cross-section. It's perforated, and it's got rock-wool fill. And it's about 42% open area. So the big struggle there was the mechanical designer said, this is a cooling tower. I need gobs of air to make it actually work as a cooling tower instead of just an expensive fan. Yet I had to contain, because you can see through the slide here that this is the property line right at that roof rail. So, we had to get air in but contain the noise. And just for scale, this is, as if that weren't bad enough, they said, oh, well, we need UPS, uninterruptible power supply. So we're going to put in a 2-megawatt diesel generator in the basement, just in case you didn't have enough to do this week. This is the exhaust for that. It comes up 4 floors, goes out through here. That is the muffler. And you can see that's about a 36 diameter muffler, and it's about 8 feet long. And even then, we had to direct the end of it up through this little enclosure and shoot it up. This was the original cooling tower with banks of silencers. You see how close the neighbors were. So I usually say, if you paint me into a corner, I can still almost always solve your noise problem, but I might end up spending a pile of your money doing it. Let's talk early so that we don't get painted into that corner. One last story here because I'm rapidly running out of time. This was an IBM research facility in Silicon Valley. And I remember sitting for hours in a meeting where these guys argued about which $3,000 leather chairs would surround their $20,000 koa wood conference table. Guess what is directly under this fan? That video conference room. The executive director, he's got 700 PhDs working for him, researching the next big chip or disk drive for IBM worldwide. And he's trying to have conferences in there. And so this whole room is on a floated floor, a concrete floor on top of a concrete floor on springs. And you got spring isolators. I'm having real trouble with the controller here. We've got two different spring isolators because this main axial fan has a heavy end where the motor is and a lighter end. So we need two different ones. And I got this call, and they said, Earl, we turned on this fan. You had to spend thousands of dollars and go to all this trouble to make the noise go away. We turned it on, and it sounds like a 747 in this conference room, and the executive director is getting his hatchet. He's looking for you. So I got on a plane and flew down there, and we're going to zoom in a little bit. What happened, in retrospect, it was almost comical, but it wasn't very funny at the time. When they put these springs in, they jack up the whole inertia base in the fan, and they use these big 1.5-inch diameter nuts to support it while they slid the springs in and bolted them, and then they were supposed to let them off and level them. Well, what you can't see in this picture is if you got down and shone a light up under, it's still sitting on those 4 hard points of contact. It's not actually riding on the springs. The guys installing it put the springs in, then the lunch whistle blew. They came back an hour later, and they said, oh, we just need to torque down the bolts here, and it looks level. We don't even have to adjust it. And they walked away. So as soon as we jacked that up and pulled those out, and I used to bring one of those to these tech talks. I'm traveling light today. As soon as we pulled those out and it went down and we leveled a little bit, the noise went away in the conference room. So quality control is my enemy. You got to do it 99.9% right, or else you don't get most of the benefit. And I'm going to kind of skip through a lot of the rest of this. And I'll leave you with this last thought. Call me. You have my card now. And if you didn't get one, I'll make sure you can. If you didn't get a handout, I gave it to the ASHRAE folks here, and they can get it to you, or you can just send me an email, earl@mullinsacoustics.com, and I'll send you the handout for today, that tidbits thing. By the way, looking through that handout, is there anything that really jumps out and it really shocks you, something you thought you knew that? I intended to spend about 5 minutes just going over that handout. I guess not. Okay.
I have a question. What did you do on the federal?
Well, what we did on the Levi building is ultimately none of this enclosure was there in the first place.
Oh,
We built this enclosure around it, had air intake through the silencers, it had air exhaust through the louvers, and it even had to have a roof on it because of the homes up on the hill here. So all of this stuff that you see is noise control added just to take care of this one little cooling tower. And that's been a while. And it worked. At that point, I could measure 50 decibels at night at the property line, and the judges were satisfied, and we didn't spend the month in jail.
What was it before?
About 62, 63.
All of us at property line?
Most noise ordinances say at residential properties, thou shalt not exceed 60 decibels during the day and 50 decibels during the night. And since this is 24/7 computer equipment, their whole server for all of Levi Strauss Corporation, it was 24/7 facility. So we had to work to the nighttime limits.
And what's that sound? What is that? That's about acoustic.
Well, who's got the meter? We'll be quiet for a second, let us settle down. Tell us what it reads.
52.
About 52. So this is the nighttime noise limit at a residential property line in San Francisco and hundreds of other jurisdictions. So if you've got a piece of equipment sitting out next to you, you know, I grew up in a home that was literally right next door to a Detroit Edison substation. And we could hear relays clicking in and out and transformers. I thought it was cool, especially when things went wrong. And we saw sparks and woke up at 4 in the morning with the fire trucks in our lawn.
So in Boise, it's 100 decibels. Oh, there's a property line in Boise, right?
We don't really have much of a noise ordinance here in Boise. What it says is, thou shalt not hear amplified music or voice. If it's audible at the sidewalk or within 50 feet of the venue, that's really all it says. We don't have a numerical limit, and that's real common. I run into that all the time where jurisdictions, yeah, feel free to leave if you need to. We've gone over our time, but as long as you guys are attentive and you're asking good questions, I'll keep talking until you throw me out.
So what if you had a situation where, say, a chiller, air-cooled chiller outdoor, right next to a condominium or student housing or something like that? It's going to be disruptive. What's maybe not jurisdictional law that's allowed, but if there's complaints for the owner to take care of that?
There are various things I can do. Sometimes we can build an enclosure around it, around a couple of sides, from getting from the chiller to the facade of the building. Sometimes we use a silencer package. Sometimes we just put it in a remote location. That's why it's a good thing to ask the question early, because you turn the thing on and realize you have a noise problem. It's kind of expensive to fix.
Here in Boise, if that was the case, it was disruptive to the neighbor, can they cause a complaint and force the owner to mitigate it?
Well, anybody can complain about anything, but we have pretty almost non-existent ordinance here in Boise, so it'd be hard to compel you. You know, downtown San Francisco is pretty easy. You go and measure. If you can hear the thing and it's 51 decibels, you're in violation. They cite you, and it's up to you to fix it. But we're not that well developed here. Yes.
You got a piece of equipment that stays 70 decibels and 5 feet away. What is it at, like 1 meter?
Great question, and blast one of the slides. Basically, the rule of thumb is the sound level drops off by 5 or 6 decibels. 6 theoretically, 5 every time you double the distance. So if your equipment was 70 feet, it's going to drop by 5 decibels at 10 feet, 5 more at 20 feet, 5 more at 40 feet, so on. So distance can really be your friend. Putting something really close to something noise sensitive is a recipe for minor disaster, at least, maybe major disaster. Question? The question was, is there an advantage to using thicker lining, say 1.5 inches versus 1 inch? Inside an enclosure, yes, the thicker lining will help absorb more low frequencies. Lower frequencies are very long wavelength, and the thicker the lining, the more of the lows you absorb. But there's a practical limit. You know, it's probably a nickel solution to a dollar problem. It's not going to fully solve the answer or the question. So, you know, there are times when I will tell a mechanical designer, hey, based on what I see here, we need 1.5 inch or 2 inch duct liner. I regret doing that because I realize that he needs an ID to move air. And so if I say 2 inch duct liner is drew by 4 inches in both dimensions, and that could be a real problem in most buildings. Okay, well, I'm in Boise. You've got my card. If anybody needs the handout, just you know, either give me your email before you leave, and I'll take care of it. But thanks for your attention. Thanks for having me. Thanks to you folks on the web. I hope you learned something.